In the silent reaches of the cosmos, where galaxies drift like ancient embers and time stretches thin across the void, a single anomaly emerged, quiet, distant, and impossibly real. It appeared in the dark, where the universe hides its oldest secrets. A place ruled by laws so precise that even starlight obeys them without question. Relativity bends the fabric of space. Quantum fields hum beneath every particle, and the great expansion pulls worlds apart with the rhythm of a cosmic tide. Yet, somewhere beyond the familiar scaffolding of physics, something flickered out of alignment. The anomaly did not behave like matter. It did not behave like energy. It moved as if gravity had forgotten its purpose, as if time itself hesitated and tried to flow in two directions at once. Instruments across Earth's observatories recorded a signature no star should produce. A light curve bending before its source existed. A shadow warping spacetime beyond the strength of any known mass. A whisper of energy rising from what should have been absolute nothingness. For a moment, scientists wondered if their machines had malfunctioned, but the anomaly persisted, steady and indifferent. Refusing to fit into any equation written since the dawn of modern physics, if this discovery were real, then something deeper than understanding was at stake. Einstein's elegant geometry, the quantum fabric beneath reality. The very constants that anchor existence, all of them trembled before this silent defiance. And so the question rose from the darkness itself. What happens when the universe reveals something that should be impossible, yet undeniably exists? In the quiet hours before dawn, when most of the world still slept beneath drifting city lights, a stream of data began its slow descent to Earth. It came from a machine that never slept. A mirror circling the sun 1,000,000 miles from home, the James Webb Space Telescope, like a lantern held at the universe's edge. It surveyed regions where time itself had grown thin, gathering the faint whispers of galaxies born when the cosmos was still young. On that night, its gaze had drifted toward a field chosen for its silence. No nearby stars to drown the view, no swirling gas to confuse the instruments, no gravitational disturbances to bend the signals. It was a region selected for calibration, for simplicity, a place where the universe ought to behave exactly as expected. But buried in that deep, ancient darkness was a single point of light that should not have been there. It appeared first as a statistical irregularity, a minor one, subtle enough that most algorithms dismissed it as cosmic noise. But noise does not repeat itself across multiple exposures. Noise does not grow brighter over a sequence of hours. And noise does not carry the spectral fingerprint of an object. Older than the laws governing its existence, at the Space Telescope Science Institute, the data landed in the inbox of Dr. Lena Arendt, an observational cosmologist known for her habit of questioning everything, even her own equations. She was reviewing deep field imagery intended for an unrelated study, the early clustering of protogalaxies. When the anomaly caught her eye, it was a small deviation, almost unworthy of attention, but it carried a signature that felt out of place. As if something in the cosmos had briefly tugged at the fabric of reality, she zoomed in, expecting the anomaly to resolve into an imaging artifact. A misalignment in the detectors, a cosmic ray streak. But it did not. Instead, it sharpened, becoming something frighteningly specific. A brightness curve rising and falling with the strange precision of a heartbeat. She blinked, thinking it a trick of exhaustion. But the curve remained. Objects in the early universe should not pulse. Their light should stretch and redden under the tyranny of cosmic expansion. And yet the anomaly flickered with the clean symmetry of something recent. Something orderly, something young, but it was not young. Lena's breath caught as she ran a redshift analysis. The algorithms processed the faint spectrum, comparing its wavelengths to known cosmic signatures. Moments later, the estimated distance appeared on her screen, 13.2 billion light-years. That would place the object near the dawn of the first galaxies, long before the universe should have formed anything stable enough to pulse. It was a time of chaotic formation, collapsing clouds and violent births of stars so massive they lived only a few million years before dying in fire. Nothing then was gentle. Nothing was precise. but the anomaly pulsed like a pendulum. She immediately flagged the data and forwarded it to her team, requesting independent verification. Within hours, confirmations arrived. The object was real. Its signal was genuine, and though faint enough to be nearly swallowed by cosmic dust, it was unmistakably coherent, a structured rhythm woven into the fabric of space-time. Still, one anomaly does not make a discovery. Instruments can deceive. Algorithms can misread. So the team turned to another sentinel of the cosmos, the Laser Interferometer Gravitational Wave Observatory, LIGO. While Webb surveyed light, LIGO listened for ripples in space-time itself, the trembling footprints of cosmic collisions. On the night the anomaly was recorded, LIGO's detectors had registered a faint signature, too weak for official classification. But strangely synchronized with the timing of Webb's data, the correlation was almost impossible. Light and gravity do not always travel together, nor do their echoes align with such mathematical precision. Yet the timestamps overlapped within milliseconds, as if the anomaly had whispered in light and trembled in gravity at the very same moment. That coincidence alone was enough to draw the attention of Dr. Arjun Malik, a theoretical physicist who spent years studying the boundary between quantum mechanics and relativity, a boundary where paradoxes tend to gather like storms. He was accustomed to strange numbers, but these numbers carried a tone that unsettled him. The gravitational signal displayed a curve far too smooth to belong to known astrophysical events. It lacked the chaotic crescendo of black hole mergers, the thunder of neutron stars spiraling into one another, the violent peaks that accompany cosmic catastrophes. Instead, the curve resembled something steady, deliberate, almost engineered, as if space-time itself had oscillated with intention. Arjun cross-referenced the data with cosmic ray observatories, searching for any stray particles arriving at energies beyond theoretical limits. And there, hidden within ice cubes, neutrino logs from the South Pole, he found the third whisper, a neutrino. One of the universe's most elusive messengers had struck the Antarctic ice at an energy level that defied explanation. Too high for any known stellar process, too clean for random background flux, and too perfectly timed to dismiss. Light, gravity, and neutrinos, three pillars of cosmic communication, all reacting to something in the deep darkness. At the same instant, three independent instruments had witnessed the same impossible event, and yet none of them agreed on what the object could be. Lena believed it might be a star, but no known star pulsed with such precision. Arjun suspected a topological defect, a relic from the early universe, but those relics should have decayed long ago. Other researchers proposed exotic compact objects, dark matter fluctuations, or even primordial black holes. But each model contradicted at least one piece of the data. The anomaly refused to fit. Weeks passed, and the initial disbelief hardened into scientific unease. Researchers began running simulations, feeding the anomaly's light curve into models of stellar dynamics. None meshed. Quantum field equations were tested, modified, stretched, and still they snapped under the weight of the numbers. What troubled scientists most was not the anomaly's brightness or distance, but its coherence. The light exhibited a pattern that suggested two incompatible realities. The object seemed both impossibly ancient and impossibly young. Its spectrum carried the reddened signature of the early universe, stretched across billions of years, yet its pulse rate indicated a structure no older than a stable star. To exist, it would require conditions the universe had not yet created at that time. It was like finding the heartbeat of a child inside, the bones of a fossil, and this contradiction awakened an old fear, that the universe might not be as chronological as it appears. That time, under certain conditions, might layer itself like sediment, one present lying atop another. But such speculation demanded more data. Teams began requesting Webb's instruments to return to the anomaly's coordinates. Days later, they received new imagery. This time, the anomaly had changed. Its brightness curve had shifted slightly, not dramatically. but enough to suggest motion, or perhaps decay. The spectrum showed faint new lines, indicating a temperature drop of several million degrees. And yet, its redshift remained the same. An object cannot cool rapidly without releasing tremendous amounts of energy. Yet there was no sign of such release. No jets, no outflows, no surrounding nebula shaped by heat. It was cooling. Silently by now, the anomaly had drawn attention from institutions across the world: NASA, ESA, the Kavli Institute for Cosmology, the Max Planck Institute. Each group brought their own theories, their own tools, their own doubts. Still, the greatest disbelief came from those who understood cosmic history best. Experts in early universe physics argued that stable, pulsing objects simply could not exist so soon after the Big Bang, the cosmic microwave. Background had only just started to cool. Matter had only begun forming the first atomic structures. Gravity was still sculpting the scaffolding where galaxies would eventually grow. There should have been nothing then, but chaos hot. Violent, formless, yet the anomaly moved with the quiet confidence of something crafted. And slowly, as more eyes turned toward it, the darker question formed: had humanity witnessed the signature of a structure older than the first stars, yet behaving with the precision of something newly made? Arjun proposed a controversial possibility. Perhaps the anomaly was not in the early universe. Perhaps it only appeared to be. Redshift could be manipulated under extreme gravitational conditions. Light could stretch if passing through warped spacetime regions unknown to current models. But such conditions would require objects of impossible mass, structures that should collapse into black holes but somehow resisted doing so. A star that was not a star. A mass that was not a mass. A signal that moved as though time itself had uncertain direction. Lena hesitated to accept such theories. She preferred explanations grounded in known physics, even stretched to their limits. But each attempt to anchor the anomaly within standard models ended the same way, with contradictions. The anomaly's existence threatened to unravel more than calculations. It challenged the assumption that the universe follows rules consistently, that its behavior at the beginning reflects its behavior now. Order, humans believed, always risen from chaos in predictable ways. But this object whispered the opposite, that order might have come first, and chaos after. When the research teams presented their preliminary findings at an international symposium, the room was filled with an unease that was not fear of the unknown. This was no supernova, no black hole merger, no ancient relic from cosmic inflation. It was something else entirely. A discovery that hinted at a deeper architecture beneath reality, one not bound to linear time, its classical matter, or even the stable vacuum state of the universe. In that moment, as equations faltered and models fractured, a realization began to take shape. The universe had revealed something it was never meant to reveal, a signal from a structure that should not exist, a heartbeat from a past that could not contain it, a whisper from the very edge of physical law. And the scientists who first glimpsed it understood that they were standing at the threshold of a discovery that did not merely challenge physics, it threatened to break it. The first wave of disbelief came quietly. It drifted through the halls of observatories, whispered across conference calls, and settled uneasily in the minds of physicists who had spent their lives trusting the universe to behave in predictable ways. But predictability is a fragile illusion. Beneath the surface of certainty lies a cosmos built on delicate balances. Balances that, once disturbed, unravel the very fabric of understanding. The anomaly did not simply challenge a theory, nor did it expose a gap in a model. It struck at the pillars that hold modern physics upright, and with every new measurement, those pillars began to tremble. The first fracture appeared in the conservation of energy. The rule that commands every star, every atom, every heartbeat. In the universe as known, energy cannot arise from nowhere nor vanish without trace. It shifts form light to heat, its motion to radiation, but its sum never changes. Yet the anomaly radiated with a luminosity inconsistent with any known fuel source, shone too brightly for its mass, too steadily for its age. too coherently for the violent epoch from which it seemed to originate. Models predicted it should have collapsed or dimmed billions of years ago. Instead, it glowed with a vigor that defied every calculation. If energy conservation held, the anomaly should not shine at all. If the anomaly shone, then energy conservation faltered. For many scientists, that alone was enough to cause unease. But the anomaly held more disturbances, deeper, stranger, more dangerous. The second fracture came with relativity's sacred limit, cosmic speed cap imposed by Einstein himself. Nothing, no matter how determined, accelerates beyond the speed of light. It is the absolute boundary of motion, the edge past which meaning evaporates. Even gravity, subtle and all-pervading, respects this limit. Its waves carry distortions. Of space-time outward, at exactly light speed, never faster. Yet the correlation between the anomaly's light curve and LIGO's gravitational reading contained a timing discrepancy that no one could reconcile. The gravitational tremor had arrived just slightly too early, not enough to trigger an alert, but enough to unsettle the researchers who compared timestamps with trembling hands. If gravitational information reached Earth before its luminous counterpart, then space-time itself had allowed gravity to outrun light. And if gravity could do so under extreme conditions, the universe was not bound by the rules written into relativity's geometry. A universe where gravity travels faster than light is a universe without causality, where effects might precede their causes. And the fundamental ordering of reality becomes unstable. The third fracture came from the world of quantum fields, the invisible ocean beneath existence. According to modern physics, every particle is a vibration in one of these fields, delicate ripples in an invisible sea spread across all of space-time. Quantum fields are stable. They must be stable. If they were not, matter would not exist. But the anomaly's neutrino signature, that impossibly energetic particle caught beneath Antarctic ice, carried a troubling implication. The neutrino's energy exceeded the maximum predicted by known quantum interactions. It was as though the field that produced it had briefly surged, amplifying itself above the stable ground state of the universe. Such amplification should be impossible. If a field rises too far above its stable state, it triggers runaway decay. Entire regions of space-time collapse into a more stable configuration, a phenomenon known as false vacuum decay. One of the most catastrophic ideas in physics. If it ever occurred, the universe as known would vanish instantly, and yet the anomaly had emitted a particle suggesting a momentary departure from stability. Without triggering collapse, how did the universe allow such an event? Why did the cosmos not unravel at its seams? This question haunted the quantum physicists who studied the data late into the night. Staring at graphs whose lines told a story they refused to believe, the fourth fracture came from cosmic expansion models, the frameworks that describe how galaxies drift apart as space stretches beneath them. For decades, astronomers measured this expansion using redshift, the stretching of light into longer wavelengths as it travels across expanding space. The anomaly's redshift was impossible. It's too high for its luminosity, too clean for its coherence. It's too old for its structure. Redshift normally tells the story of distance and age. The farther an object, the longer its light has traveled, and the older its signature becomes. But the anomaly's behavior contradicted this logic. Its redshift placed it near the birth of the universe, yet its pulse rate was characteristic of something young and stable, an ancient object behaving like a newborn star, a newborn structure sitting in the universe's first breath. It was a contradiction without resolution. The cosmic expansion model, the map of space-time stretching, simply could not place the anomaly in any consistent timeline. Every scientist who reviewed the data encountered the same unsettling reality. The anomaly did not belong anywhere in the universe's chronology. And if chronology itself faltered, so too did the foundations on which all cosmological models depended. More contradictions emerged. The anomaly's apparent mass, estimated through lensing distortions of background light, exceeded the limits of neutron stars but lacked the signature of a black hole. Its gravitational curvature was too strong for normal matter, yet too weak for singulars. It a cuboid middle ground, a mass that should not exist in any stable form, a weight that bent space-time more sharply than stars, but not enough to form an event horizon. It was as if the object were playing by rules the universe had not yet revealed. Some researchers wondered whether it represented a new class of compact object, neither neutron star nor black hole nor white dwarf, but something unimagined. Others feared it might be the shadow of a deeper structure, partially concealed by dimensions unaccounted for in current models. But every explanation collapsed under scrutiny. Mass too high, lensing too perfect, temperature too inconsistent, signal desynchronized. A quiet dread settled over the scientific community. If the anomaly were genuine, then Einstein's relativity, quantum field theory, cosmic inflation, dark matter, dark energy, the standard model, and the known shape of spacetime itself were incomplete at best, and false at worst. A discovery that required the rewriting of physics was unprecedented. Even the earliest revelations, black holes, quantum tunneling, cosmic microwave background radiation, had complemented or expanded existing theories. But this anomaly did not expand physics. It contradicted it in meetings across the world. Researchers sat in muted rooms, staring at screens displaying curves and spectra that defied comprehension. Some argued it must be a measurement error. Others suggested an uncalibrated detector, a computational artifact, or an observational coincidence. Yet each attempt to dismiss the anomaly died the same slow death. Every independent instrument had seen it. Every international team had confirmed it. Every recalibration still yielded the same impossible result, and so disbelief turned into something heavier, a collective hesitation, a shared fear of the implications. A universe where the anomaly was real was a universe where cherished laws became approximations, where certainty dissolved into speculation, where humanity's understanding was revealed to be only a thin veneer stretched over a much deeper truth. Physicists do not fear the unknown, but they fear the impossible because the impossible hints that understanding might be fundamentally out of reach. In private conversations, some scientists whispered that perhaps the anomaly was a message from the universe itself, a reminder that human theories were never meant to describe all of creation, only the parts that behaved politely. Others worried that if this anomaly existed, more might follow, and the next could be far less gentle.
Ow.
If the cosmos could support objects violating conservation laws, outrunning light, destabilizing quantum fields, or contradicting expansion models, then the universe was far more dynamic, unstable, and perhaps dangerous than previously imagined. A small group of theorists proposed a startling interpretation. Perhaps the anomaly was not an object, but an event, a temporary tear in the fabric of spacetime, a glitch in the universe's memory, a place where physical law folded in on itself. The idea was dismissed publicly. Quietly it lingered. Astronomers replayed Webb's data, tracing the flicker as though searching for intent. Astrophysicists reanalyzed the gravitational wave curve, searching for hidden harmonics. Particle physicists scrutinized the neutrino signature for signs of exotic interactions, but the anomaly remained an unsolved equation, a riddle carved into the cosmos long before humanity's arrival. Slowly, one realization settled across the global scientific community. If this anomaly is real, then the universe has broken its own rules, or revealed rules humanity has not yet imagined. Either possibility carried profound consequences. Physics was no longer a map of cosmic certainty. It had become a doorway, one opening into territory vast, wild, and unexplored. Scientists had always believed that the universe was intelligible, that its laws were universal, and its behavior predictable. But now, staring at the impossible pulse of the anomaly, many felt a quiet shift in perspective. Perhaps the universe was not a machine governed by fixed equations. Perhaps it was an evolving entity, rewriting itself as it expanded. Perhaps physical law was not rigid but emergent, a temporary order rising from deeper, hidden forces. The anomaly's quiet defiance forced humanity to ask a question it had avoided for centuries. What if the laws of physics are not laws at all? Only interpretations of a story the universe is still learning to tell. With this realization, the true shock of the anomaly became clear. It was not the brightness, or the redshift, or the strange coherence of its signal. It was the possibility that the universe was not finished, and that somewhere in its vast ancient depths, something moved with intentions unknown, something capable of challenging the very foundations on which reality stood. Scientists understood, and that they had stepped onto the threshold of a new era. Not an era of answers, but an era of deeper questions. For the anomaly did not simply break physics. It broke the illusion that physics had ever been complete. In the weeks that followed the scientific shock, the anomaly ceased to be a curiosity and became a global priority. The world's observatories, optical, gravitational, quantum, cosmic, turned their instruments toward the same silent point in the sky. What began as a single flicker of impossible light evolved into an orchestrated pursuit, a worldwide effort to interrogate the universe where it seemed to contradict itself. The James Webb Space Telescope focused on the region first. For days it stared into the darkness, collecting photons older than most stars. What Webb returned was unsettling. The anomaly continued to pulse, but the rhythm had shifted. Tiny variations, less than 1 part in 10,000, appeared in its oscillation. These were not random fluctuations. They followed a subtle structure, rising and falling in a pattern that hinted at deep mathematical order. A whisper of repetition began to form, as though the anomaly possessed an internal mechanism. Something stable enough to persist across cosmic ages, yet flexible enough to evolve. As Webb observed in infrared, the Fermi Gamma Ray Space Telescope watched in high-energy wavelengths. What it recorded could not be mistaken for coincidence. Over multiple observation windows, Fermi detected faint bursts of gamma radiation, aligned in time with Webb's pulses but with a puzzling twist. Each burst arrived ever so slightly ahead of the corresponding light pulse, by margins too precise to be noise. It was as though the high-energy emissions were anticipating the lower-energy light. Like an echo that arrived before the sound it should follow. These discrepancies led some researchers to suspect that SpaceTime, in the anomaly's region, might not behave uniformly. Perhaps something within that distant corner of the cosmos allowed certain forms of energy to travel more freely than others, slipping through folds or gradients unseen in ordinary space, while space telescopes monitored the sky. Detectors far beneath Earth's surface joined the investigation. In Antarctica, the IceCube Neutrino Observatory sat embedded in a cubic kilometer of transparent blue ice, listening for ghost-like particles that could pass through planets as though they were smoke. IceCube's preliminary data had already hinted at an impossibly energetic neutrino associated with the anomaly. Now, with repeated monitoring, a new pattern emerged. Every time the anomaly pulsed, IceCube recorded a cluster of neutrinos, tiny, almost imperceptible, but unmistakably connected. These neutrinos possessed energies that made little sense, too high for known astrophysical processes, yet too consistent to be random. Even stranger, their arrival times formed a staggered sequence, as though different neutrino flavors were being peeled from the same event across subtly shifting intervals. To the physicists studying the data, this behavior bore an uncomfortable implication. Neutrinos rarely interact with anything, yet these behaved as if passing through regions where the rules governing their oscillations, rooted in quantum field stability, briefly changed. It was as if the space around the anomaly allowed particles to adopt energies they should not, as though something within that region had the power to tilt the quantum vacuum itself. Meanwhile, the twin gravitational wave detectors of LIGO and Virgo continued their vigil. Their readings remained faint. But the anomaly's gravitational signature developed a peculiar trait, a periodic modulation, a steady undulation woven into the background hum of spacetime. Gravitational waves usually announce violent cosmic collisions. They roar, peak, and vanish. But this signal murmured. It repeated. It behaved like a wave trapped in a vast resonant chamber, oscillating between dimensions of curvature that no simulation could fully represent. Some theorists suggested that the anomaly might be interacting with a structure in spacetime itself, perhaps a relic from the early universe, like a cosmic string or a fold in the fabric left behind by inflation. If so, The anomaly was no mere object, but a phenomenon sitting atop a deeper fault line in reality. As data accumulated, patterns converged across independent instruments. Webb saw shifts in the anomaly's pulse. Fermi saw gamma echoes preceding light. IceCube saw neutrino cascades synchronized to those pulses. LIGO and Virgo saw gravitational tremors woven into the same rhythm. And CERN, thousands of kilometers away in Europe, added another piece to the puzzle. At the Large Hadron Collider, researchers had begun cross-analyzing the anomaly's data with results from high-energy collisions. Their goal was to see whether any known particle, behavior however exotic, could replicate the anomaly's energy signatures. Instead, they found something far stranger. In rare collisions, detectors recorded traces of events that momentarily violated expected conservation patterns. Faint divergences in missing energy that echoed the anomaly's own discrepancy. These were tiny deviations, invisible unless compared to thousands of events at scale. But when matched against the anomaly's signatures, the shape of the divergences appeared hauntingly similar. It suggested that whatever governed the anomaly might also appear in extreme conditions on Earth, albeit fleetingly like shadows cast by a deeper phenomenon passing through both the cosmos and the quantum world. With this growing network of correlations, researchers began to see the anomaly not as a singular event, but as part of a repeating pattern. They traced similar faint irregularities in archival data gamma-ray bursts that arrived too early, neutrino flashes whose directionality seemed inconsistent, gravitational murmurs dismissed as instrument glitches. These events were scattered across decades of observations, each too subtle to claim as anything more than noise at the time. But now, with the anomaly as a Rosetta Stone, these fragments formed a new picture. The anomaly had siblings. It had flickered before. It had echoed in distant skies long before modern instruments were sensitive enough to notice. The phenomenon was not new. Humanity was simply unprepared to recognize it. A deeper question arose. Was the anomaly signaling a structure woven through cosmic history, one so faint and strange that only now, with modern tools, could it be seen at all? As research intensified, the nature of the anomaly itself came under renewed scrutiny. Spectral analyses revealed that its temperature fluctuations were inconsistent with any known astrophysical body. They behaved instead like the thermodynamics of an open system, one shedding or absorbing energy without following stellar evolution models. Matter within the region seemed to shift states with unnatural speed, cooling where it should heat, brightening where it should dim. Such behavior hinted at a possibility that many researchers approached with hesitation. The anomaly might be leaking energy across boundaries not accounted for by three-dimensional space. In models involving higher dimensions proposed by string theory and various quantum gravity frameworks, objects could, in principle, exchange energy with dimensional neighbors. If the anomaly resided near such a boundary, or partially extended into it, its unusual behavior might represent a kind of cosmic interaction never before observed. Others considered an even more unsettling scenario. Time within the anomaly's region. Light might not be stable. Temperature shifts, pulse variations, and signal distortions could be signatures of temporal gradients regions, where the direction or flow of time differed subtly from its surroundings. In such environments, energy could appear to behave unpredictably, simply because the timeline of its emission lacked uniformity. This idea, while speculative, found faint support in LIGO's data. The gravitational tremors carried minute distortions resembling phase shifts, offsets suggestive of time-like curvature, the kind predicted in theoretical models of wormholes or SpaceTime folds, but the data contained no evidence of a traversable structure. The anomaly did not behave like an entrance, a tunnel, or a collapsed object. It behaved instead like a Skara-localized region where the fabric of spacetime bore tension, as if twisted by forces from outside the observable universe. As global teams worked together, one conclusion grew difficult to avoid. The anomaly did not merely trigger contradictions in physics side, provided hints toward a new architecture underlying reality, a framework in which energy, gravity, time, and quantum fields could behave in ways far more flexible than previously believed. Yet for all the data, the question remained: what was the anomaly? A star that defied physics? A relic of cosmic inflation? A dimensional fracture? A temporal scar? A signal from a deeper structure? Or something stranger, something that rendered such labels meaningless? As the world's instruments continued to monitor the anomaly, one final discovery deepened the mystery further. While cross-referencing Webb's most recent observations with IceCube neutrino bursts and Fermi gamma sequences, a team of data scientists identified a faint pattern in the timing intervals, one that repeated across multiple wavelengths, particle detections, and gravitational distortions. The anomaly's pulses were not random. They were not merely rhythmic. They formed a sequence of progression with mathematical structure. It was subtle, only drowned in cosmic noise, but unmistakable once seen. A pattern encoded in the spacing of light pulses, in the gaps between neutrino arrivals, in the harmonics of gravitational fluctuations. A pattern that hinted at neither decay nor stability, but process. The anomaly was not a glitch. It was not a relic. It was not a mistake. It behaved like a phenomenon unfolding across multiple layers of reality-leaking energy, bending space-time, triggering quantum irregularities, and repeating a sequence whose meaning remained opaque. A map, some whispered. A message others dared to suggest. A structure, deep and ancient, revealing itself through fractures in physical law. Whatever it was, one truth became clear. The anomaly pointed toward something deeper than physics had ever imagined, a hidden scaffolding of the universe itself, revealed only through its failures, and humanity, for the first time, stood at the threshold of understanding not just the cosmos as it appears, but the cosmos as it is. As weeks turned into months, the anomaly no longer behaved like a distant oddity confined to a single region of the sky. It began to reveal a far more troubling nature, one that reached beyond its isolated pulse and seeped into the structure of the cosmos itself. What once appeared as a localized contradiction now unfolded into a pattern. And patterns, in the language of the universe, are rarely accidents. The first sign of escalation came from the James Webb Space Telescope. While monitoring the original anomaly, Webb detected a faint shimmer in a different sector of the sky, a flicker so subtle it would have been ignored under normal circumstances. But its signature was unmistakable. It pulsed with the same impossible rhythm, the same unnatural coherence, the same quiet defiance of astrophysical law. It was weaker, further, partially obscured by cosmic dust. Yet it was there, a second anomaly, separated by billions of light years, and behaving exactly like the first. No known phenomenon, natural or theoretical, should replicate itself with such precision across cosmic distances. The universe is not a place of perfect repetition. It is a realm of chaotic births, uneven evolutions, and unpredictable interactions. Yet these anomalies were synchronized as if governed by a hidden clock ticking beneath the visible cosmos. When Webb turned its instruments toward a third region, a field studied years earlier without incident, it found that the archive data had changed. A pulse appeared where none existed before, embedded retroactively within the recorded images. Scientists compared timestamps, checked for manipulation, reviewed data integrity. Nothing had been altered. Yet the anomaly had inserted itself into the past. Like a shadow appearing in a photograph long after it was taken, the scientific community recoiled. Objects may appear. Signals may arrive late. But the past does not rewrite itself. Or so it was believed. Meanwhile, LIGO and Virgo detected gravitational tremors more frequently, not loud enough to signal cosmic collisions, but structured to dismiss as noise. Their patterns echoed the anomaly's rhythm, forming a growing network of space-time distortions that stretched across the sky like invisible chords on a cosmic instrument slowly coming into tune. And then came the most disturbing clue. The tremors were increasing in amplitude. Not dramatically, not enough to disrupt planets or damage Earth, but enough to suggest that whatever force underlay the anomaly was strengthening. Spacetime itself seemed to be vibrating with a coherence that had no precedent in cosmology. Some theorists began whispering that the anomaly exhibited signs of quantum coherence on a cosmic scale, a phenomenon believed to be impossible. In the quantum world, coherence allows particles to behave as a unified system, sharing states and information instantaneously. But coherence fades as systems grow larger. At macroscopic scales, it collapses. At the scale of stars, galaxies, or cosmic voids, coherence should be utterly impossible, and yet the anomalies flickered with unity. 3 points of light, 3 gravitational tremors, 3 neutrino cascades, all aligned in a pattern too complex for coincidence, yet too deliberate for chaos. To some, the implications were terrifying. If regions of space-time were becoming quantum coherent, then the boundary between the macroscopic and quantum worlds was dissolving. Physical laws that depended on scale, thermodynamics, relativity, classical mechanics could unravel. The universe itself might behave like a single quantum entity, reshaping probability at scales never imagined. Others saw a different threat. Signs that the anomaly mimicked the signature of a false vacuum fluctuation. A false vacuum represents a metastable state of the quantum field, a local minimum that is not the true ground state of the universe. If disturbed even by the smallest fluctuation, it could collapse into a lower energy state, converting the entire cosmos into a new configuration of physics. This hypothetical collapse would travel at the speed of light, instantaneous and unstoppable, rewriting the laws of nature as it spread. For decades, false vacuum decay had been a theoretical curiosity, mathematically possible, but unlikely to occur within the universe's lifespan. But the anomaly's temperature fluctuations, energy discrepancies, and space-time distortions began to resemble simulations of pre-collapse conditions. Not perfectly, not conclusively, but disturbingly close. Some researchers feared they were witnessing the early stages of vacuum instability. Others believed the anomaly was a scar left by such an event long ago. A few dared to ask whether the universe had undergone such transitions before, changing its laws like a living organism adapting through cosmic ages, as if echoing these fears. The anomaly continued to evolve. Webb recorded fluctuations in its spectral lines, suggesting that fundamental constants such as the fine structure constant that governs electromagnetic interactions were subtly different in its vicinity. The deviations were microscopic, buried within measurement error, yet consistent across repeated observations. Even a tiny shift in fundamental constants would be catastrophic. If the fine structure constant changed by 1%, atoms could not form. If Newton's gravitational constant shifted, stars would collapse or fail to ignite. If the Higgs field fluctuated, particles would lose their mass. Yet the anomaly's region behaved as though the constants were drifting not wildly, not enough to destabilize matter, but enough to suggest that the constants of physics might not be constants at all. The philosophical terror grew. If physical laws varied across space, then the universe was not uniform. If they varied across time, then physics itself might evolve. And if they varied in the anomaly's presence, then something deeper than law, something older than symmetry, was exerting influence. The dread lay not in destruction, but in revelation. What if the universe was not governed by universal laws? What if the laws were merely local agreements, temporary and fragile? What if stability itself was an anomaly, a fleeting equilibrium in a deeper sea of shifting realities? Researchers began to see the anomaly not as a challenge to physics, but as a window into a hidden foundation on which physics rested. A crack in the cosmic veneer that exposed a darker, more fluid architecture, and beneath the beauty of that revelation lay a quiet terror. If this phenomenon spread, the universe, as humanity knew it, might not survive, not through violence, not through collapse, but through transformation, a transformation that had already begun. In the aftermath of the anomaly's deepening revelations, the scientific world found itself suspended over an abyss of possibilities. The data no longer pointed toward a single explanation, nor did it align cleanly with any established theory. Instead, it fanned outward, like the branches of a cosmic tree, each path leading toward a different vision of reality. Some wondrous, some unsettling, and some threatening to the very concept of existence. And so, researchers began assembling the possible explanations, layering evidence with imagination, fact with speculation. None could claim certainty, yet all carried the weight of scientific rigor. What emerged was not an answer, but a constellation of theories, glowing with its own strange potential. The first theory rose from the idea that the universe, vast as it is, may not be alone. For decades, multiverse models had hovered at the edges of cosmology, mathematical curiosities, elegant frameworks that offered solutions to problems the observable universe could not. Most remained untestable, hidden behind the silence of cosmic horizons. But the anomaly changed that. Its synchronized pulses, its drifting constants, its scattered siblings appearing across possible distances, all pointed toward a phenomenon inconsistent with an isolated universe. Some researchers began to wonder whether the anomaly represented multiverse leakage, a place where the boundaries between universes grew thin. In such regions, the fabric of spacetime might brush against that of a parallel world, allowing signals, energy, or even fundamental constants to bleed through the divide. If this were true, then the anomaly was not simply a structure within this universe. It was an artifact of interaction and echo produced where cosmic walls touched. Such leakage could explain the drifting fine structure constant observed in the anomaly's vicinity. If neighboring universes possess slightly different physical laws, then their influence could subtly distort the constants of this one. In models involving bubble universes formed during eternal inflation, such interactions were rare, but not impossible. The boundaries between universes, though vast and ancient, might occasionally deform under unknown pressures. If universes touched, even briefly, the resulting disturbances could propagate as pulses of altered physics, rippling across space-time like waves across the surface of a pond. The anomaly's repeating rhythm, its synchronized behavior across the cosmos, could represent a global imprint of such contact, cosmic handshake between realities. But while beautiful, this theory posed its own unsettling questions. If universes could influence one another, then the stability of physical law could no longer be taken for granted. What appears constant here mass charge gravity might be at the mercy of forces beyond this universe's jurisdiction. The anomaly could be the first whisper of a larger shifting of cosmic boundaries. The second theory delved not into parallel universes, but into the universe's own internal architecture. Some physicists saw in the anomaly's gravitational tremors and retroactive signals the signature of exotic spacetime topology, a fold, tear, or hidden curvature left behind by the early universe. During cosmic inflation, spacetime expanded faster than the speed of light, stretching quantum fluctuations into macroscopic structures. Some of these structures, theorists believed, could have formed stable defects, cosmic strings, domain walls, warp-like folds connecting distant regions. These relics would be unimaginably dense and rare, yet powerful enough to distort light, matter, and even time. If the anomaly sat atop such a defect, its strange behavior could be the byproduct of warped geometry. Light traveling through a folded region could emerge with altered timing, producing the retroactive pulses seen in Webb's archived images. Gravity passing through a spatial crease could arrive early, echoing Leo's anomalous detection. Neutrinos skimming the edges of a topological defect could oscillate with impossible energies. In this model, the universe had scarce fault lines etched into its fabric from an era when physics itself was young and volatile. The anomaly might be the first clear detection of such a scar, still active, still bending space-time in ways that defied classical intuition. Some researchers pushed this idea further, proposing that the anomaly might sit near the throat of a primordial wormhole. If so, the synchronized pulses across cosmic distances could represent light entering and emerging from different mouths of the same structure. The universe might be far more interconnected than it appeared. woven with hidden conduits older than stars themselves, but such structures, if real, also carried danger. Wormholes required exotic matter with negative energy densities, substances not known to exist naturally. And topological defects, if brought into motion, could slice through space-time like cracks spreading across ice. The anomaly might be a stable relic, or the beginning of an unraveling. The third theory emerged from the most catastrophic corners of quantum field theory, false vacuum instability. It suggested that the universe might not reside in the lowest possible energy state. Instead, it could exist in a metastable condition, a precarious plateau, where fields rested temporarily, vulnerable to collapse. In such a scenario, fluctuation of sufficient magnitude could trigger a transition to a lower energy vacuum. The consequences would be unimaginable. The laws of physics, the nature of particles, even the dimensional structure of space could change as the universe reconfigured itself. The event would propagate at light speed, silent and unstoppable. The anomaly's temperature shifts, energy imbalances, and spectral distortions resembled certain simulated pre-collapse conditions. Not perfectly, nothing in the real universe ever matched equations. Exactly, but close enough to unsettle even hardened physicists. Perhaps the anomaly was a region where the vacuum had begun to deform a bubble of unstable field configuration. Or perhaps it was a relic of a collapse that had already occurred elsewhere. Its shock waves slowed or frozen by exotic space-time conditions. If true, the anomaly was not simply a threat. It was a message from the quantum foundation of reality itself, a reminder that existence, seemingly solid, rested on fragile footing. The fourth theory centered on quantum field anomalies. Every particle, every force, every fundamental interaction emerged from fluctuations in quantum fields permeating space. These fields were assumed stable, uniform, and predictable, but the anomaly challenged that assumption. Its spectrum contained energies that should not exist. Its neutrinos carried signatures suggestive of field amplification. Moments when the vacuum energy surged beyond the stable ground state without causing collapse. Some theorists believe the anomaly represented a region where quantum fields resonated with each other, producing energy spontaneously, like harmonics emerging from a plucked string. In such regions, virtual particles might appear with real energy. Photons might gain mass. Gravity might weaken or strengthen in response to fluctuations. The anomaly's pulses could be the breath of a vacuum oscillating, rising and falling in a rhythm set by deeper laws than those of particle physics. The fifth theory emerged from relativity's shadows. Relativity breaking scenarios. Some saw in the anomaly's timing discrepancies, evidence that time near the structure flowed differently, dilated more strongly than general relativity predicted. Gravity might be influenced by unseen dimensions, causing distortions that altered the speed of information. If time itself wavered in the anomaly's presence, then nothing within it could be trusted to obey classical ordering. Causes might separate from effects. Pulses might arrive before they were emitted. And constants might drift not because they change in space, but because they change in time in such a universe. The anomaly was not a structure, but a symptom evidence of a cosmos. Whose temporal integrity was beginning to fray. Each theory pushed the boundaries of understanding. None offered certainty. All revealed a universe far stranger than once imagined. As the anomaly deepened into a threat, a clue, an omen, or a revelation, depending on whom one asked, humanity recognized that observation was no longer enough. The cosmos had revealed something that resisted every law written to explain it. Something that bent space-time, distorted constants, and echoed across the universe with a coherence that defied the very meaning of distance. And so the scientific world entered a new era, one defined not by passive discovery, but by pursuit. The universe had taken the first step. Humanity would take the next. The first response came from the architects of gravitational wave astronomy. LIGO and Virgo had already detected faint murmurs from the anomaly's region, subtle oscillations woven into the cosmic background like the trembling of an invisible drum. But these detectors were never designed for phenomena such as this. They were built to capture the violent roars of colliding black holes. not the delicate heartbeat of something that should not exist, to probe deeper. Scientists accelerated plans to construct next-generation gravitational wave arrays instruments of unprecedented sensitivity. Among them rose the vision of the Einstein telescope, an underground triangular observatory capable of detecting space-time distortions 1,000 times weaker than current limits. It would listen not only for the explosive events that shaped galaxies, but for the quiet sighs of space-time itself, the subtle modulations that might reveal the anomaly's inner workings. Alongside it, plans for LISA, the Laser Interferometer Space Antenna, pushed forward with renewed urgency. Orbiting millions of kilometers from Earth, LISA would detect gravitational waves with periods stretching minutes to hours, exactly the range in which some of the anomaly's strange patterns seemed to lie. Its trio of spacecraft would drift in a silent cosmic dance, forming an interferometer the size of a planetary orbit, sensitive enough to detect the faint curvature of space-time where the anomaly's influence lingered. If the anomaly carried a gravitational signature, LISA would hear it clearly. While gravity was being pursued in space, the search for elusive particles intensified beneath the surface of the Earth. The Ice Cube Neutrino Observatory, buried in the frozen depths of Antarctica, had already played a crucial role by detecting neutrinos coinciding with the anomaly's pulses. But Ice Cube, vast as it was, had limitations. Its detectors were spaced too widely to capture fine-grained structures in neutrino bursts. And so the next evolution began. IceCube GN2, an expanded array stretching across even greater volumes of ancient ice. This new observatory would offer unprecedented clarity sensitive enough to detect the subtle flavor oscillations that might reveal whether neutrinos passing near the anomaly underwent transformations unknown to the standard model. If quantum fields in that region fluctuated, if vacuum states shifted, if energy leaked between dimensions, the neutrinos would carry the imprint. In Japan, the Hyperkamiokande detector prepared to search for the same signatures from beneath mountains of stone. Millions of tons of ultra-pure water would sit in darkness, waiting for the faint flashes of light produced when neutrinos grazed their surfaces. Its depth, isolation, and sensitivity made it capable of detecting even the rarest interactions. Interactions that could reveal whether the anomaly had begun influencing particle behavior across the universe. Above Earth, the eyes of humanity widened. Plans accelerated for next-generation space telescopes, each designed to peel back different layers of reality. The Nancy Grace Roman Space Telescope would map cosmic expansion with extraordinary precision, searching for distortions that hinted at drifting physical constants. Athena, the Advanced Telescope for High-Energy Astrophysics, would probe the XR universe for patterns in the anomaly's high-energy emissions. And beyond these, a new vision emerged. Telescopes equipped with quantum sensors, capable of detecting minute fluctuations in space-time curvature. Based on entangled atoms and superconducting circuits, these instruments could measure gravitational fields so faint they bordered on the theoretical. If space-time near the anomaly wavered even slightly, quantum sensors would feel its tremble. No single instrument could capture the phenomenon alone, but together they formed a global symphony of observation: gravity, light, neutrinos, and quantum fields, all watching, listening, measuring the unmeasurable. Meanwhile, deep beneath the Franco-Swiss border, humanity attempted something unprecedented. At CERN's Large Hadron Collider, researchers began designing experiments that mimicked the anomaly's signatures. They accelerated particles to energies approaching the limits of current technology, colliding them with precision to search for behaviors that echoed the impossible neutrino energies or light distortions seen in the anomaly. They created magnetic fields stronger than any found on Earth, forcing particles into paths that warped spacetime at microscopic scales. They measured vacuum fluctuations with sensitivity so high that it brushed against the fabric of quantum uncertainty itself. In these collisions, the detectors saw hints fleeting, fragile, but unmistakable, the same pattern found near the anomaly: missing energy that could not be explained. Particles appearing with properties slightly out of alignment with known physics and quantum fluctuations that suggested a temporary departure from the stable vacuum. None of these results proved anything on their own, But every measurement added a stroke to the emerging portrait of a universe behaving as though influenced by forces beyond current understanding, and to bring these scattered efforts into harmony, scientists turned to simulations. Vast computational networks, some earthbound, some operating on quantum processors, attempted to recreate the anomaly's behavior. They fed in data from telescopes, neutrino detectors, gravitational arrays, and particle colliders. They adjusted constants, rewrote equations, tested scenarios that bent physics to its breaking point. Simulations where gravity weakened, simulations where time folded, simulations where quantum fields resonated like strings in a cosmic harp, simulations where universes brushed against each other. Most models failed instantly. Some held for seconds. A few lasted for hours, long enough to suggest that the anomaly was not random, but structured. As these tools evolved, another realization began to take root. The anomaly was forcing science to evolve with it. Instruments once designed to study distant stars now hunted for deviations in the constants of nature. Detectors built to observe particles now searched for signs of vacuum instability. Arrays created to listen to black hole collisions now listened to the faint whisper of a phenomenon that might predate the stars themselves. Humanity had always shaped tools to study the universe. Now, for the first time, the universe shaped the tools to study itself. The pursuit was no longer observational. It was transformative. In the quiet that followed the surge of data, theories, instruments, and global collaboration, something changed in the scientific world. The urgency did not fade, nor did the mystery lose its sharpness. But amid the calculations and the feverish anticipation, a deeper silence emerged, the kind that arrives when humanity stands at the edge of understanding, peering into a truth too vast to grasp fully. The anomaly, once a distant flicker in the cosmos, had grown into a mirror, reflecting something uncomfortable. The limits of knowledge itself persisted beyond equations, defied predictions, and refused to belong to any framework designed to explain the universe. It was not hostile, nor was it passive. It simply existed, quiet, steady, inscrutable. And in that simple existence lay a question that had haunted every discovery since the dawn of curiosity. What if the universe tolerates far more than humanity is able to comprehend? For centuries, physics had been built upon the assumption that nature's laws were immutable fixed commandments governing the behavior of matter, energy, space, and time. These laws offered comfort, forming a scaffolding around which human understanding could grow. From Newton's falling apple to Einstein's curvature of spacetime, each revelation tightened the structure, reinforcing the belief that the cosmos was intelligible. But the anomaly pointed toward a different reality, one where laws might shift, fluctuate, or fracture, where constants might drift, where time might quiver, where dimensions might brush against one another like veils stirred by wind. It hinted that the scaffolding of physics was not eternal stone, but something more fragile, something provisional, perhaps even something alive. As researchers studied the anomaly, they found themselves returning to questions long buried beneath mathematics, questions once asked by mystics, poets, and philosophers. Now rising from the heart of science itself, was the universe finished, or was it still unfolding? Was reality a static masterpiece, or a work in progress? Were the laws of nature the rules of creation, or simply its habits? The anomaly offered no answers. Instead, it posed a possibility both terrifying and beautiful, that humanity might be witnessing the universe rewriting itself not violently, not abruptly, but subtly, like an artist revisiting an old canvas. Some physicists began considering whether the cosmos, in all its vastness, might be capable of self-modification. After all, stars transformed hydrogen into heavier elements, forming the building blocks of planets, oceans, and life. Black holes reshaped space and time, altering the geometry of the universe. Quantum fields fluctuated endlessly, birthing particles from nothingness. Perhaps the anomaly was another expression of this creative force, one operating on scales far beyond human imagination. If so, then the universe was not broken. It was evolving, and evolution, whether cosmic or biological, was never gentle. It pushed boundaries, challenged assumptions, and rewrote what was believed to be permanent. The anomaly might be such a momentous cosmic inflection point where deeper structures revealed themselves through the cracks in existing theory. Some scientists feared this revelation. They saw in the anomaly a threat to stability, a sign that physics might be mutable. If gravity could behave differently in one region of space, what prevented it from shifting elsewhere? If time could flow differently near the anomaly, what kept it uniform across the cosmos? If vacuum energy could fluctuate dangerously, what ensured the safety of existence? Yet others felt awe, not fear. To them, the anomaly was an invitation, a doorway into realms of understanding that humanity had never dared explore. They argued that the laws of physics were not eternal truths, but approximations, shadows of deeper realities. The anomaly did not invalidate science. It expanded it. It whispered that the universe was far richer than the equations used to describe it. As the data grew deeper and the mystery more profound, researchers found themselves contemplating not only the structure of the cosmos, but humanity's place within it. For so long, the universe had seemed indifferent, vast, cold, unchanging. But the anomaly introduced a sense of dynamic unpredictability. A reminder that existence was not mechanical, but creative. What if the universe was not a machine? What if it was a story, one still being written? This idea, though poetic, resonated strangely with the scientific evidence. The anomaly behaved neither like a star, nor a particle, nor a black hole. It behaved like a process. Something unfolding. Something interacting with deeper layers of reality. Something expressing a change invisible to human senses, yet undeniable to human instruments. And so, scientists began reconsidering the nature of truth. Perhaps the universe did not present itself through fixed foundations, but through shifting patterns. Perhaps certainty had always been an illusion useful for survival, but not reflective of cosmic reality. Perhaps the anomaly was less an exception and more a reminder that the universe had always been stranger than anyone dared believe. As this perspective grew, so did a new form of humility. Humanity had long imagined itself progressing toward a complete understanding of Natura final theory. A unified framework, a cosmic key that unlocked everything. But the anomaly suggested that such completeness might be impossible, not because the universe was hostile, but because it was boundless. Infinite in depth, infinite in structure, infinite in potential. Even Einstein once admitted that the most incomprehensible thing about the universe was that it was comprehensible at all. Now, faced with the anomaly, the scientific world began to see that comprehension itself was only a thin veneer over an ocean of unknowns. And yet, within that ocean lay beauty, not chaos. The anomaly did not destroy. It did not erase. It revealed that physics was not rigid stone, but living clay. It revealed that reality extended far beyond perception. It revealed that existence itself was layered, dynamic, and mysterious. And in that revelation, scientists found something rare, a sense of wonder untainted by certainty.